about just the slides.
Yeah, that's right. You want to power up? Okay, so we're going to roll right away because, as you can tell, we're slightly behind schedule, but we will be making up some of this time. So our next presentation is by one of our most recently affiliated faculty. Shreyas has been with Purdue for a little while, and we end up being at a dinner together one time, and oftentimes even on campus I say, oh, I'm with CERIAS, and they say, unless they are already affiliated with us, now what is CERIAS? I had told Shreyas, I'm with CERIAS. He goes, I've been meaning to talk to you. I think my work aligns with the center. And we sure enough, we met, and right away was blown away by the research. And so even though this is his very first semester affiliated with us, I sought him out and said, please, you need to come present your research because I think there's a lot of people who'd be interested in it. So welcome.
Thanks, Joel. Can everybody hear me? All right, great. So yeah, thanks very much for the invitation. It's been a fantastic symposium so far. So my name is Shreyas Sundaram. I'm a professor in the Electrical and Computer Engineering School here at Purdue. My background is in control theory, and so I approach problems, especially the security problems I'm going to be talking about today, from that perspective. So my research team, our focus is on analysis and design of large-scale network systems, okay? And so we come at it from a theoretical perspective. So we specifically are interested in the interplay between the topology of these networks, or the structure of these networks, and the dynamics that are occurring on top of those networks. Okay, you can't understand what's happening in these large-scale networks without really considering the interplay between both of these things. And so we look at these types of problems and try and understand what a global type of behavior occur in these networks based on the combination of these two. And these large-scale networks, you can think of them in a variety of application domains, right? You can think of large-scale robotic swarms. You could think of large communication systems, power grids, or other infrastructure networks. You can think about social networks, right? So these are all just large-scale networks. So one of the important things that I'm going to be talking about, focusing on today, is the role of these networks in facilitating information spreading and coordination. Okay, so this is one of the most important functions of a network. And so you can think of, for example, in social and economic networks, as the information representing things like ideas or knowledge or opinions, fads, and so forth. So how does this spread throughout the network? Or if you're looking at engineered networks, you can think about data, measurements that are being gathered at the various nodes, computations that are being done, different control signals that are being computed, etc. And based on this information, whatever the underlying network happens to be, you can talk about different special cases of information dissemination or coordination tasks. Right? So the simplest one perhaps is data accumulation. Maybe you just want certain nodes in the network to gather all of the information in the network. You can talk about consensus type problems where you want all of the nodes in the network to agree on something related to their individual data. Okay, so for example, if these are a social network, maybe you want everybody to come to the same opinion based on their initial opinions. If this is, for example, the smart transportation networks that we were talking about earlier in the panel, maybe you want all the vehicles to agree on a common speed and so forth. You can talk about distributed optimization, where nodes have individual utility functions, and maybe the nodes want to cooperatively figure out what the best thing to do is based on all their individual utility functions. You can talk about state estimation problems, where there's a big physical process that's being monitored by these different nodes, and they all get different measurements, and they're trying to coordinate to figure out what the state of the underlying process is. Okay? So you can think about all these different types of coordination and information dissemination tasks. And for all these types of questions, the natural types of things to look at are, can the network diffuse information quickly, efficiently, reliably, and so forth? And in particular, what I'm going to be focusing on is what happens if certain nodes in the network don't play along, right? So what happens if they behave maliciously? How do you overcome this? What are the things that we should be looking for in these networks, and what kinds of algorithms will allow us to give some guarantees in the face of malicious behavior? So because I want to be talking at a mathematical level, we're going to sort of abstract away the details of the specific applications here. So this is going to be different from perhaps the other talks we've seen here. So I'm going to be working at a higher level of abstraction. And so we're going to be thinking about a network just as a graph with n nodes, v1 through vn. Okay, and these nodes could represent whatever the physical thing is in the network that you're interested in. And there's going to be edges between the nodes. So an edge from vi to vj means that vi can send information to vj. Okay, and each node I has access to some local, potentially private information, right? So if this is a sensor network, maybe these are the measurements that they're taking. If this is a social network, maybe these are the opinions of the individuals. Maybe it's a large data set that each node has. If you think about sort of large-scale machine learning type of problems, they're all gathering tons of data, and this information corresponds to the data sets. So I'm going to be focusing on consensus for most of the talk because it's a very simple problem, but it's going to illustrate most of the concepts. So consensus basically says every node in the network has some initial value, xi of 0. And it's maybe useful to think about this in terms of social networks because we can easily imagine it. So imagine that you're this network and everybody has an initial opinion, okay, which is xi of 0. So at every time step t, so every day, each node in the network talks to its neighbors and updates its value as an average of the values in its neighborhood. Okay, very simple, right? So you talk to your neighbors, you update your opinion as an average of your neighbor's opinion. So you can mathematically represent it like this. So there aren't going to be very many equations, and if they are, there's going to be very simple equations like this. So basically this says the value of node I at day t plus 1 is just some convex combination or some weighted average of the values of itself and its neighbors. Okay? So you can imagine if everybody in the network keeps doing this over and over again, everybody will, in fact, asymptotically converge to the same opinion, right? And it turns out it's pretty easy to prove this. And so one of the nice things about algorithms like this is that the nodes don't need to know anything about the network, right? They're not explicitly routing information back and forth. They're not saying, hey, I want to tell Jim that my opinion is this, so route it through this path and so forth. This is just sort of diffusive algorithms where every node just talks to its neighbors and updates its value over time based on what it's getting from its neighbors, and information diffuses through the network to lead to some global behavior. Okay, so you can extend this sort of very simple algorithm, this sort of diffusive algorithm, to account for things like distributed optimization, machine learning, state estimation, and so forth. Okay, so but the core of these types of algorithms ends up being these sort of simple diffusive consensus type dynamics. Great, so this is, if everybody does this, everybody's going to reach consensus on some opinion. What happens if certain nodes in the network decide they're not going to do this? Right? So you can have nodes that fail or are compromised by an adversary and just behave in arbitrary ways, or perhaps worst case ways. These attacks could be coordinated to try and disrupt whatever the network is doing. Okay, so we're going to be looking at, for example, Byzantine attacks where the nodes can just update their values however they want. They can send arbitrary information to their neighbors and so forth. So it turns out these classical diffusive algorithms are very vulnerable. So if everybody does this, everybody sort of talks to their neighbors, updates their opinion every day, everybody converges. If there's even one stubborn node in the network that decides it's never going to change its value, no matter what its neighbors say, turns out if everybody else followed the dynamics, everybody will converge to the value of that stubborn individual. Okay, we all know this from our organizations, probably. So you wouldn't want to implement this, right? I don't think you would want to implement this. So what do we do about this? How can we think about making algorithms, these sort of simple algorithms that spread information through networks, more resilient against misbehavior? Very simple misbehavior, but even more complicated misbehavior like this. Okay? So now clearly the problem of resilient information dissemination and consensus is very old, right? It goes back to the computer science literature from the 70s and 80s. Okay, and there's some fundamental properties and limitations that have been identified in the literature, which we cannot overcome, but it'll be useful to think about those limitations and the classical way of thinking about these problems. So it's just to make sure everybody's on the same page, I'll just go over that briefly. So suppose you have a network that looks like this, just 4 nodes. Okay, and node 1, for whatever reason, wants to obtain node 3's value or calculate some function of node 3's value. Okay, node 3's value is actually 7. Now in this network, there's only 2 ways for information to go from node 3 to node 1, right? Through node 2 or through node 4. And suppose node 2 decides it doesn't want node 1 to figure out what node 3's value is, so it's going to participate in whatever algorithm you specify, whatever dynamics you posit for this network, by pretending that node 3's value is something else, let's say 9. Right? Now, so node 1, it's going to be looking at the information it's getting from node 2 and 4 about node 3's value, and if it looks over here, it says, hey, it looks like node 3's value is 9. If it looks here, it says, hey, it looks like node 3's value is 7. Okay? And unless it has some a priori reason to believe one versus the other, it's never going to be able to resolve this ambiguity. Okay? So in this case, a single malicious node has succeeded in preventing some other node from accurately or reliably calculating some function of some other node's value. Right? And what is the problem here? Node 1 really needs a tiebreaker in this network to be able to resolve this ambiguity. So this is where the notion of graph connectivity comes in. So this is a classical way to measure resilience of networks. Okay, so the connectivity of a network is basically just the smallest number of nodes that you have to remove to disconnect the network. So over here, this network has a connectivity of 1 because I just have to remove 1 node to disconnect this network. This network has a connectivity of 2 because I have to remove at least 2 nodes. And this network has a connectivity of 3 because I have to remove at least 3 nodes. Okay? And this is sort of a structural property. This is saying, is the network going to remain connected after I remove a certain number of nodes? But there's a nice sort of theorem in graph theory, which is called Menger's theorem, which basically says if the connectivity is R, that means that there are R different paths in the network between any 2 nodes. Okay, so here, for example, the connectivity is 3, and no matter what 2 nodes you choose, there's 3 different ways for information to spread. And that's useful because then you can say things like, hey, if I wanted to send information from here to here, I could send it along this path, and this path, and as long as at most one of the paths is corrupted, the guy at the other end is going to be receiving 2 pieces of information that match, and they can reliably obtain the information. Right? And so that's basically the underlying principle behind classical ways of looking at this. If there are up to f bad nodes in the network, any 2 nodes can reliably exchange information if and only if the network is 2f plus 1 connected. Okay? And this is basically the simplest way to think about it, is just send information along these 2f plus 1 different paths. And I'm going to, as long as there's at most f bad guys in the network, I'm going to guarantee to be receiving f plus 1 copies that are the same. And if I do that, I'm going to take that to be the accurate value. Okay? But implicitly in what I said there's this underlying assumption that the network is known and fixed, and I can route information through this network, and I'm sitting there and I'm expecting information from somebody on the other side, and so forth. So there's this sort of fixed network topology, a lot of data storage and computations and routing and so forth that's assumed in these classical results focusing on connectivity as a metric. Okay, so what we really want to focus on are scalable algorithms that don't really require the nodes to know anything about the network topology. Right? We want to be able to this to work in time-varying networks if these are vehicles or smart cities, where nodes come and go and so forth. We'd like to be able to tolerate many malicious nodes. Right? So in these giant networks, it doesn't make sense to say I want to be able to tolerate 3 bad guys in the entire network. I want to be able to have the number of bad guys potentially scale with the size of the network. Okay, and in certain applications, in distributed optimization, for example, if you're gathering local data, you don't necessarily want to be sharing the data with other people, right? So this could be private data, it could be massive amounts of data. So again, you want to not just send information from point to point, but you want sort of diffusive algorithms. So here we're going to talk a little bit about what we can do to go back to those sort of diffusive consensus algorithms and make them more resilient. So let's think about this. So the previous version of the algorithm said, every day you wake up, you listen to all your friends, you update your opinion as an average of all their opinions. But I have pretty crazy friends. Why should I take all their opinions into consideration, right? So instead, let me assume that there are up to f bad guys, f crazy people in my neighborhood. I don't know who they are. What I'm going to do is I'm going to ignore the extreme opinions in my neighborhood. So I'm going to remove the highest f, lowest f, and just average the rest. Okay? So ignore the crazies, average the moderates. So you can model that in this way. It looks exactly the same as before, except now instead of including all your neighbors, you're just including the moderate opinions in your network. Okay, is that clear? Okay. So what would happen under this very simple algorithm? Okay, so it turns out people have looked at this kind of algorithm in the computer science literature in the 80s, but only for special kinds of graphs, like complete graphs where everybody can talk to each other and so forth. And only recently have we been able to characterize very crisp conditions on network topologies that allow dynamics like this to succeed. And to think about what those network conditions are, it's very useful to consider an example like this. So suppose that you have a network that looks like this. So you have n over 2 nodes here. Half the nodes are here. Half the nodes are here. These are very sort of closely knit communities. Okay, everybody knows everybody else. So everybody's connected to everybody here. Everybody's connected to everybody here. And everybody in each community has one friend in the other community. Okay, so they're connected to one node in the other side. So now suppose everybody here starts with an initial value of 0. Everybody here starts with an initial value of 1. And everybody throws away one highest and one lowest values in their neighborhood at each time step. So what's going to happen here? So this person is going to wake up. She's going to say, I have a bunch of friends who say 0. I have one friend who says 1. I throw away the highest and the lowest, and I average the rest. And her value stays 0. Everybody here stays 0. Everybody here stays 1. Okay? So under this very simple modification of the algorithm, where I'm just throwing away one highest and one lowest, consensus is not reached in this network. This is a beautiful network from the perspective of classical metrics. Okay? Everybody's connected to half of everybody else, half of the nodes in the network. The connectivity of this network is n over 2. So if I wanted, you'd have to remove n over 2 nodes to disconnect this network, and I could tolerate n over 4 bad guys if I were to use classical routing schemes. But using these very simple local diffusive schemes, there aren't even any bad guys in this network, and yet nobody reaches consensus. Okay, so that's kind of bad news, right? So this algorithm seemed kind of cool where we're just kind of throwing away values. We don't need it to know anything about the network, but it's not working in networks like this. So what is the problem? What is it about this network that caused this consensus algorithm not to work? Okay, now if you think about it, what happened was that we could take this network and we could split it into 2 sets, where even though each of those sets collectively had enough information coming in from the other set, individually, no node in that set had enough neighbors outside its own set. Right? So individually, each node was throwing away the only useful information it was getting from outside that set. So this was essentially the bottleneck that prevented this type of algorithm from working. So what we want to do is we need to come up with a new topological property. Connectivity is no longer a sufficient property to be able to reason about things like this. So we need to come up with a new graph property that will allow us to be able to say what networks have bottlenecks like this and what networks don't. Okay? Any questions so far? Okay, great. So here's how we came up with this graph property. So suppose I give you this network, okay? And suppose I give you some subset of nodes. We say that that subset is R reachable if it contains a node that has R neighbors outside that set. Okay, so let's think about this. So if I give you this subset, this greenish subset here, this subset is 3 reachable because it has a node, V5 in this case, that has 3 neighbors outside that set. Okay, so this set is 3 reachable. This set is 4 reachable because it has a node that has 4 neighbors outside that set. So essentially, a set being R reachable means that there's some node that has enough neighbors outside that set, where enough is given by R. Okay, so that's a set property, but we want to be able to reason about graphs. Okay? So we say a graph is R robust if no matter how I choose 2 different sets of nodes, at least one of the sets is R reachable. So for example, here, no matter how I choose 2 subsets of nodes, say I pick these 2 subsets, at least one of these sets has a node that has 3 neighbors outside this set. Okay, and so if I check this for all possible pairs of sets, I'll find that that's true. And so we say that this graph is R robust. Is that definition clear? Okay. So the reason why we defined it this way is because, remember, what caused us to fail when we looked at that other graph? We were able to find 2 subsets where neither subset had a node that had enough neighbors outside its own set. So we want to be able to define our robustness to say no matter how I choose 2 different subsets, at least one of the subsets is going to have a node that has enough neighbors outside that set, so I don't run into the problem that I ran into earlier. Okay, so given that, then here's the main result. So if the network is now 2f plus 1 robust as opposed to 2f plus 1 connected, then this sort of simple diffusive algorithm where I throw away highest f, lowest f, and average the rest is guaranteed to cause all the regular nodes that actually follow this algorithm to converge to consensus. That consensus value is going to be reasonable in the sense that it's guaranteed to be between the largest and smallest initial values of any regular node. Okay, so this means that the bad guys can't cause the consensus value to be some arbitrarily large value. And this is going to happen despite the actions of any f local set of adversaries. And what does f local mean? F local means that you can have up to f bad guys in the neighborhood of every good guy. Okay, not just a restriction on the entire network, but you can have many, many, many bad guys in the entire network, and this will be this algorithm will guarantee that property as long as the robustness condition is satisfied on the network. Okay, so here's an illustration. So essentially, this is an example of distributed optimization, but you have a bunch of regular nodes here, and the value close to 0 is the actual true optimal value of the functions that they're trying to optimize here. But we're going to see a bunch of bad guys show up in this network. Okay, and these bad guys are just going to do arbitrary things. Here we have them doing sinusoids. But you'll notice that no matter how many of these bad guys show up here, the good guys still are doing the right thing. Compare this to what we saw earlier, where a single stubborn node, regardless of how big the network was able to corrupt the values of all the other nodes. Okay. And so this is a nice scalable algorithm in that this is going to work no matter how big the network is. So it's worth thinking about this graph property that we identified, right? So we said, so how did we get here? We said we want to come up with this algorithm that allows these nodes to coordinate despite bad guys. We came up with an algorithm, and then we identified a graph property that's required for the algorithm to succeed. But this graph property seems kind of interesting on its own. It seems like a really strong graph property, right? And so our robustness is a much stronger property than our connectivity in general. We saw that network that was n/2 connected, but it was just one robust. It didn't allow these dynamics to succeed. So the structural interpretation is the following. An R-connected network, just to refresh your memory, means that the network will remain connected even after any R-1 nodes are removed. An R-robust network will remain connected even when up to R-1 nodes are removed from the neighborhood of every remaining node. So you could remove a ton more nodes from the network and still be guaranteed to remain connected. So this is giving us a new metric for evaluating and designing networks, right? So if we want to design networks so that they're able to tolerate a large number of failures, maybe we don't just go back to the classical idea of R connectivity. Maybe we should be designing them to be R robust. Okay, and so here's an example. If I give you this network and I say, how many nodes can fail here and have the network still be connected? Classically, if I go back to my graph theory and I go back to my sort of computer science class, I would say, let me calculate the connectivity of this network. In this case, the connectivity is 2. Okay, I'd have to remove these 2 nodes to disconnect the network. So I'm only guaranteeing you that the network will stay connected if I remove 1 node. But it turns out this network is too robust. So I could actually remove any one local set. I could remove 1 node from the neighborhood of every remaining node, and I still guarantee you that the network will remain connected. Okay? So everything looks great. It's one problem. Okay? It's co-NP complete to determine whether a given network is R robust. So if I walk up to you with a Facebook graph and I say, is this R robust? Good luck. Right? I have no idea how to solve this. So it's difficult. It's computationally difficult, unless P is equal to NP, to be able to calculate the robustness of given networks. However, it is easy to design R robust networks for any given R. Okay? And what's more surprising is that there are many mathematical models for large-scale networks. These are typically random graph models. So you can generate billions of nodes and put the edges between the nodes randomly according to some distribution to model different types of networks. And in these networks, in these random networks, you have to add edges with a certain density. You have to add a certain number of edges in order to be able to get connectivity. It turns out that for these types of random graphs, the number of edges that you have to add to get connectivity actually also makes the graph R robust. So if you're getting a certain level of connectivity, you're actually getting R robustness for free. Okay? And so this was surprising to us, but what this is saying is that these mathematical models, at least for large-scale networks, possess a lot more structural robustness than previously identified. You could remove a ton more nodes from these networks and still have them succeed, more than you would have predicted by just focusing on connectivity. All right, so just to summarize then, what we've been looking at is, again, the interplay between topology and dynamics. We were interested in identifying scalable algorithms, diffusive algorithms to allow nodes and networks to coordinate and overcome bad guys. So we came up with this algorithm based on local filtering, where nodes sort of throw away highest and lowest values and average the rest. We came up with conditions on the topology for which such an algorithm would succeed. We came up with this property of R robustness. And this sort of thing that we stumbled across, right, we just sort of tripped across this property. It turns out this is a pretty cool property. So it gives you a lot of strong guarantees on networks, and many networks actually possess this property when we didn't realize it before. So with that, I'll take questions.
So everybody understood that, right?
Hopefully.
Any questions for Shreyas?
Jeremiah Blucky, Purdue University. NP completeness just means that some instances are hard. Is it possible maybe that for a Facebook graph or some other social network that we're interested in, there might be some customized algorithm to
Absolutely.
find?
Yeah,
Okay.
yep. And so the random graph results are actually telling you that the average instances are easy, probably. Yeah, because almost all graphs end up having this property.
Okay.
Exactly.
Thanks.
Yeah.
Is there a way, if you start with a random graph, you can converge it into an R-robust graph?
So it'll depend on how that random graph was generated. Okay, and so essentially, for example, if you look at the classical random graph, which is the Erdős-Renyi random graph, where you basically have a bunch of nodes, you flip a coin for each edge, and if it lands heads, you put that edge, and if it doesn't, you don't put it there. If that probability is high enough, you're guaranteed that it'll be R-robust on its own. If the probability is too low, then essentially it means you're going to have to add a whole bunch more edges to do that. So depending on the way that the random graph is generated, the answer to your question is going to depend on that. Yeah, because for random graphs, essentially a lot of it is related to the density of the edges or the number of edges in that graph. And so, yeah.
Yeah, I was thinking about some random traffic situation and he wants to obtain some R-robustness
Right.
out of it.
Yes.
Eventually,
Yes.
as cars leave and others
Yes.
come in.
Yep, so we have looked at that specific version of that. So one class of random graphs that helps to model that kind of situation is geometric random graphs. Essentially, you put an edge between two nodes if they're close enough together. So this models things like sensor networks or vehicles that are close together that can communicate and so forth. So at least for one-dimensional geometric random graphs, we can show that the robustness property holds at the same time as certain other very basic properties hold. Two-dimensional is much more difficult, but we believe that similar things are going to happen.
Okay, any other questions at this point? Okay, if that, we'll thank Professor
Thank you.
Shreyas Sundaram for his work.